Hi everyone, you're watching the 7th lecture of EE635 Applied Linear Algebra. I'm Deb Sattam. So, so far we have been talking about, we have started to talk about linear transformations, which are special maps from one vector space to another, V and W, both of them defined over the same field of scalars. Okay. Um, a linear map is as I said, it's a special map. It's just like an ordinary map, but it has the property that it respects the vector space structure of this V and W, right? In the last lecture, we have seen this amazing theorem about these linear maps, namely the rank nullity theorem, yeah, where we did talk about various, we gave some examples of linear maps. And then with those, we have first defined the nullity, that is the dimension of the null space, and rank of the map, which is the dimension of the image space. And there we found out that this nullity plus the rank, which is dimension of the image space, they together always is equal to, I mean, the sum of these two numbers is always equal to the dimension of the domain space, provided the domain space is a finite dimensional vector space. Okay. Now, in this lecture, we're going to see these linear maps we're going to analyze these linear maps in much more detail, yeah, in much more depth. Okay. And the starting point of today's lecture, this module, would be two special kinds of linear maps which play an immensely important role throughout this course. Okay, so in order to proceed, I first have to share my screen. Yeah, should be up now. Yes, here we are. So this is going to be lecture number 7. Okay, so this is further details, further analysis of, as I've said, linear maps or linear transformations. For brevity, we're going to call them linear maps. Let me jolt your memory. Let me recall what linear maps really are. So we have a vector space V and a vector space W, and there is this mapping phi. Yeah, this is just a mapping. What do we mean by mapping? Mapping, remember, is something that associates to each vector here a vector here. By some rule, it assigns to each vector, to each such V, a W is attached. Only one W is always attached, right? And that rule of attachment is what is known as a map. Okay. Now, this V is called the domain of the map. V is called the domain of the map. And of course, W is called the codomain of the map, right? Remember that for every V, there is some W, one W, but there is no reason why different V's should go to different W's. Yeah, two different V's can go to the same W. Also, there is no reason why for every W there should be a V. Yeah, so it may so happen that some of the W's in this code in the codomain space are not such that there is some V which get mapped to that W. Yeah, that is always possible. We can see some examples of such mapping. So before we move on to any mapping, I mean any example, it should be worthwhile to define what linear maps are. So what are linear maps? So linear maps are special kinds of such mapping which satisfy the property that, so phi is called, this is something I'm recalling from before. We have already seen this. phi is called linear map. Linear map if, listen carefully, for all v1, v2 in the vector space v, and for all alpha in the scalar in the field f, we have phi v1 plus v2 equal to phi v1 plus phi v2, and phi alpha v1 is equal to alpha phi v1. So two defining properties of a vector space, namely vector addition, closed under vector addition and closed under scalar multiplication. Yeah, these two are the defining properties of a vector space, right? So what this linear map, the characteristic property of linear maps is that it respects that vector addition and scalar multiplication, in the sense that whether you do vector addition first and then apply the map, or you apply the map first and then do the vector addition, it doesn't matter. Both are the same. Similarly, if you do scalar multiplication first and then apply the linear map, or you apply the linear map first and then do the scalar multiplication, you get the same result. So they do have exactly the same effect. Yeah, when this property is satisfied by the phi, by the map phi, we say that this map is a linear map. Yeah, is that all right? So notice that these two properties can be easily combined to get another equivalent property, namely that this property, these two properties together are equivalent to for all v1, v2 in v, and for all alpha in f, phi of alpha v1 plus v2 is equal to alpha phi v1 plus v2. You can check that this is an if and only if condition. This goes to you as a homework. This is pretty simple, straightforward check. You don't have to do too much of thinking. Just try and do this. If you don't succeed, if you face any difficulty, let me know. Yeah, please do that. This goes to you as always. Whenever you face any difficulty, just let me know. Okay, now moving on. Some examples. We have already seen various examples. The ones, if you face, any kind of confusion as to confusion in understanding such linear maps, think of them as matrices. Yeah, so our prototype for understanding vector spaces have always been these special vector spaces, like like columns of numbers, fn, fm. These are columns of numbers, n tuples, m tuples. These are our prototypes for vector spaces. Similarly, matrices are prototypes for linear maps, in the sense that suppose A is a matrix of size m cross n with entries coming from the field F. Then this A defines a linear map. A defines a linear map in the following manner. A, yeah, Fn to Fm, how any x, which is an n tuple here, it gets sent to a times x. See, this multiplication is well defined, and ax indeed is an m tuple, so it's indeed an element here. Okay, so that is how A defines a map from Fn to Fm. You can check that this is a linear map indeed. Why? A alpha x1 plus x2. This by rule of matrix multiplication, matrix vector multiplication, we know this is nothing but alpha a x1 plus a x2. So of course this satisfies the property of linear map. So therefore this map is indeed linear. Yeah, so this matrices are the basic prototype of linear maps. But this is not all. There are many other linear maps also, as we have discussed before, as exotic as like, so I define a linear map phi A from the space of all F um, um, M cross M matrices to M cross N matrices to F M cross N matrices. How? X is sent to A times X, where, so here A is already given M cross M matrix. Somebody gives you a matrix like this, I can define a linear map like that. You can check that this is a linear map, but this is a linear map from the vector space of of matrices to itself. Yeah, so this X is no longer a tuple. It's not an n tuple. It's a matrix, but still, it will this mapping will satisfy all the properties of a linear map. As we have seen that this is indeed a vector space. Yeah, and this phi a now will define a linear map. Similarly, one can also define linear map phi AB, which is a mapping once again from, let's say, f m cross n to f m cross n, which is defined as X is sent to A times X times B, where AB, so A is a given M cross M matrix, and B is a given N cross N matrix. Both are given. One can define a linear map like this. One can define, so we have already seen this linear, this Lyapunov map from, say, R n cross n symmetric matrices to R n cross n symmetric matrices, where a symmetric matrix P is sent to A transpose P plus PA. This is a linear map. Okay, so there are so many different types of linear maps available. Yeah, you should consult the book to learn about these linear maps. I mean, the various different examples of linear maps. What we are interested in this, in this in this module of the lecture is these two notions corresponding to linear maps, namely so two notions regarding linear maps. All right, what are these two properties? The first one is the so-called 1-to-1, and the second one is on-to. There are other names also. One-to-one maps are also called monic maps, or they're also called monomorphisms. On the other hand, on-to maps are also called epic maps or epimorphisms. Okay, let me define these two terms and then we will look at them more carefully. Okay, all right. So first we concentrate on one-to-one maps. I'm going to write one-to-one like this. Okay, so what is one-to-one? This is shorthand for one-to-one. So let's say phi is a linear map from a vector space V to W. By the way, before we come to this thing, let me mention this particular fact. Let me mention this particular fact that when a linear map phi, linear transformation, is from V to itself. So W is the same as V. So it takes vectors from V and maps to vectors in V. Then this phi is often called a linear operator. Operator. Instead of transformation, we call it linear operator. There are some other, what should I say, some pompous sounding names for these things also. They're also called, I think, endomorphisms. Yeah, I think they're called endomorphisms also. But let's not worry about that. When we say linear operator, you should understand that it's a map from V to itself. That's it. Just a terminology. All right. Now, coming to one-to-one maps. Yeah. So what are one-to-one maps? One-to-one, as the name suggests, phi is said to be one-to-one if phi v1 equal to phi v2 would imply v1 is equal to v2, right? Which is the same as saying, in other words, v1 not equal to v2, that is two distinct things, would get mapped to two distinct things. So if v1 is not equal to v2, then phi v1 also is not equal to phi v2. Meaning distinct things will get mapped to distinct things. That's why they're called one-to-one. One thing goes to only one. It's not many to one. Not too many different things can go to the same thing. Only distinct things will, only one thing will go to one thing. Okay? Right? So when we say one-to-one, this one in a way is fixed because it's a map. Everything has to go to only one thing, right? And in the sense that a V cannot be taken to different Ws. Phi V is only one W, right? However, what is important here is that phi v1 and phi v2 can be equal only when v1 is equal to v2. Otherwise, no. If v1 and v2 are distinct, then phi v1 and phi v2 must also be distinct. That is one-to-one. Okay? Right? Example and non-examples. So, so for a linear map, when will it be one-to-one? Right? In fact, once we see the property in more detail, we'll be able to figure out more examples. Yeah. So before, So before giving examples, let me give an equivalent condition for one-to-oneness. Yeah, and then it will kind of become absolutely clear from this ideas how to get examples of one-to-one linear maps. All right. So here is the result. Okay. The result says, so let me state this as a proposition, yeah? Phi is one-to-one if and only if null space of phi is just 0. Yeah, how do you prove this? In fact, the proof is very simple. So first, this direction, which means we assume phi is 1 to 1, we have to show that kernel phi is equal to 0. Yeah, it's very simple. Suppose this is not true. Suppose not true. This would imply there exists v not equal to 0, v in v, such that phi v is equal to 0. Yeah. So if kernel phi is not equal to 0, then there will be some non-zero vector in the kernel. Yeah, and that vector is say v. So because it's in the kernel, phi v must be equal to 0, since v belongs to kernel of 1. Okay, understand, no? So there exists v. No, instead of writing since, I think I should better write that is, yeah, v is in the kernel of phi. But notice that because it's a linear map, phi is 0 must always be equal to 0. Yeah, there are many proofs of this fact, but quick proof can be, well, you see, we have already seen for vector space theory that phi, that 0 times 0 being the scalar, no? 0 times v is always the 0 vector. This is equal to 0 times phi v because it's a linear map. So phi 0, let me write it properly, yeah? Yeah, so please bear with me. I'll do this properly. Because just two-line proof. Phi of the 0 vector is the same as phi 0 times any vector v, as we have seen before while we were defining abstract vector spaces, that 0 scalar times a vector is always equal to the 0 vector. This by the property that, by the fact that phi is a linear map, is 0 times phi v. Yeah, but this phi v is some vector in W, but this 0 is the scalar 0, so this must be, once again by the vector space properties, must be the 0 vector in W. So 0 always gets mapped to 0. So you see 0 gets mapped to 0 and V also gets mapped to 0 and V is not equal to 0, we are saying, which is a contradiction. Why? Because I'm saying it's 1 to 1, no? So everything will, two distinct things will go to two distinct things. But here I have 0 and V not equal to 0. Two distinct things are getting mapped to the same thing, namely the 0 in W. That's not okay. So this is a contradiction. This is a contradiction to phi being 1 to 1, because 0 and V are distinct, but both getting mapped to 0. So this is kind of, obvious. I mean, this is like obviously um, uh, this part of the proof, this direction, it's kind of obvious that 1 to 1 should mean kernel phi is equal to 0. Because if there is any non-zero element in the kernel phi, that also gets mapped to 0, which is a direct contradiction, direct violation of the 1 to 1 property. What is interesting is this other direction, that kernel 0 would imply this this fact that it's 1 to 1. So what we have to what we are doing here is we assume that kernel phi is equal to 0, but kernel phi is 0, that's what we are assuming. We have to show that phi is 1 to 1. So for that, what we have to show, what we have to do, this means to show that phi v1 equal to phi v2 implies v1 is equal to v2. So let phi v1 be equal to phi v2. This, as we've seen, is the same as phi v1 minus phi v2 equal to 0, right? Because I can just take the additive inverse of 5v2 and subtract this 5v2 from both sides of this equation. So this will be 0. But see, this is a linear map. This means phi v1 minus v2 is equal to 0. Yeah, by property of linear map, since phi is linear. Okay, this would imply v1 minus v2 belongs to kernel phi, but kernel phi is only the 0 vector, which means v1 minus v2 is equal to 0, since we have assumed that kernel phi contains only the 0 vector. There's only one vector in kernel phi, which is 0, so therefore v1 minus v2 must be 0, which means v1 must be equal to v2. That's what we wanted to prove, right? So this implies that phi is 1 to 1. This is the end of the proof, huh? 1 to 1 if and only if kernel phi is 0. Yeah, now you can easily construct examples. Yeah, as far as matrices are concerned, when will you get kernel phi is equal to 0? So example, say I have a matrix A in F m cross n. Yeah, this map, which is A mapping vectors in Fn to vectors in Fm, where x is sent to A times x, is 1 to 1 if and only if kernel of A is equal to 0, which means Ax equal to 0 implies x is equal to 0. Yeah, and what does this mean? Yeah, when does Ax equal to 0 mean, implying x equal to 0? What does that mean? Yeah, this means nullity is equal to 0. Yeah, this means rank of A by rank nullity theorem must be equal to dimension of V when they're finite dimensional, when V is finite dimensional. But for matrices, V is this space, which is indeed finite dimensional. Its dimension is n. In this case, this is dimension of f to the power n, which is in fact n. So rank of A is n. But you see, what is n physically? Physically, A has n number of columns. So this condition means A is full column rank. Whatever is the number of columns, that exactly is equal to the rank of the matrix. That's when it's called full column rank. Yeah, which essentially means that the columns are linearly independent. This means columns of A are linearly independent. Indeed, because columns of A as a set generates column span of A, right? Now here I'm saying that the dimension is also n. So I have n vectors which generate an n dimensional vector space. So those vectors must be linearly independent, right? Okay. So this is about one-to-one maps. When a matrix A defines a one-to-one map, it means it has to be full column rank. Okay. In fact, all these are equivalent statements. Okay, right. So this is how you get examples. The other concept is the onto concept. You know, the concept of onto maps. Okay. Yeah, onto. So let me define onto first, and then we'll see its properties. All right. So once again, phi is a linear map from vector space V to vector space W. Both are defined with the same field of scalars. Phi is said to be onto if for all W in W, there exists a V in V such that phi V is equal to this W. Yeah, that means for every W, there is a pre-image. For every element in W, there exists a pre-image of it in V under the map phi. So you remember the picture, no? That this is my vector space V, this is my vector space W, this is the mapping phi. What this says is that for everything here, there would be something here. So for everything that I have here, there would be something here which gets mapped to this thing here. That means this thing is full. Yeah, an obvious observation is the following. Phi is onto if and only if image of phi is all of W. Yeah, proof is simple. Proof is just obvious, trivially follows from the definition of onto maps. Okay, because image phi being W means, so listen carefully. Image phi is the collection of all those vectors in W for which there is a V. Now, onto says that for everything in W, there is something in V, which means everything in W is in the image of phi. Yeah? Therefore, image of phi must be all of W. That's it. Example, once again, if I look at linear maps defined in terms of, matrices. So suppose I have a matrix A, which is Fm cross n, and A once again defines this linear map from Fn to Fm by left multiplication. X goes to A times X, right? So when will this image be full? Once again, we know that uh, once again we know that okay, you see, rank dimension of kernel of A plus dimension of image of A is equal to dimension of f to the n in this case, which is just n. Okay, if image of A is full, so A is on to if and only if image of A is equal to f to the m, which is if and only if dimension of image of A is equal to m, the whole space, which then means dimension of kernel of A is plus this is m, this is equal to this n, yeah, which then tells me dimension of kernel of A is equal to n minus m. In fact, we don't even have to do all this. Yeah, it immediately follows from the fact that row rank. Okay, let me first finish, then I'll give the this other way of understanding this. So this dimension being n minus m we have already seen from row reduced echelon form that this dimension of kernel of A is always equal to n minus r, where r happens to be the row rank of A, the number of non-zero rows in the row reduced echelon form of A. What this tells us is that r is equal to m, which means row rank of A is equal to m. Yeah, in fact, these are all once again equivalent statements. So I see that this A is onto if and only if row rank of A is equal to m. In fact, we don't even have to do all these things if we sort of agree on the fact that row rank is equal to column rank, which we have already proven in the last lecture. So if row rank is equal to column rank, here column rank must be m, because column rank is the dimension of the image space, and dimension and image space is full all of f to the m. So dimension of image space of A is m. So column rank of A must be m, but row rank is equal to column rank, so row rank must also be equal to m. But what is m? Look at the matrix now. The matrix A is m cross n, so it has m number of rows and n number of columns. So row rank equal to m, this means A has its row rank exactly equal to the number of rows that it has, which means A is full row rank. Whatever is the number of vectors that we have, all of them are linearly independent. So this means A must have linearly independent rows. You see, all these are kind of dual ideas. So together, we can club these two things together, that a matrix A is the way A defines the map, where so A is an m cross n matrix, and A defines the map from f to the n to f to the m by left multiplication. In this scenario, this map is 1 1, is 1 to 1, if and only if A is full column rank. This map is onto if and only if A is full row rank. Okay. So let us close this module at this point. We'll come back in the second module to learn more about these two properties. Before we close this module and you proceed to the next module, I would like you guys to solve some immediate attention problems, which happen to be the following. So once again, on one-to-oneness and on-to-ness. Yeah. First one says, give an example of a one-to-one linear map from R2 to R2. Give an example of an onto linear map from R2 to R2. Repeat the exercise when the sizes have changed. Yeah, one more property involving involving linear maps, but abstract linear maps, no longer matrices. Yeah, no longer n tuples or 2 tuples or 3 tuples, not tuples. Abstract vector spaces, V and W. Phi is a linear map. Then prove that if phi is 1 to 1, then dimension of V must be less than or equal to dimension of W, and phi is on 2, then dimension of W must be less than or equal to dimension of V. Once again, polynomials to polynomials through differentiation, that is a linear map. Is this map onto? Is this map 1 to 1? And then, yeah, this is something that we have not done yet. Homework 1. Homework 1 will come back to homework 1 once we are done with our module number 2. Okay. Till then, let's stop this discussion now. We meet for module number 2. Okay. See you then. Bye bye.